We have to make sure we don't broadcast. It's supposed to be broadcast.
Okay, it's my pleasure to start this off. I'm David Pollard, the chair of this session. I'm going to turn over to Roland, who's going to introduce Jack.
Okay, well, thank you all for coming. And just a few words of introduction for Jack. Well, I'm sure you all know him, but some items that I might mention. Jack is from Colorado, and he arrived here some years ago, having finished his master's degree in Colorado. And he was kind of sleepy, sort of a guy at first, and I figured that was normal from Colorado. But I turned out to be soon surprised that he wasn't sleepy at all. He was just pretending. And as we will find out today, he actually took his research extremely far. I had been surprised at the time that he began. He was preceded by a very excellent student, Michael Brewer, who is probably here or coming soon today. I wondered whether I would ever have a student as good as Mike again, and found, in fact, that I did. So you are to hear from Jack today, and this is the subject. Over to you, Jack.
Great. Well, thanks for that, Roland. And I'm really excited to see so many people here today. It's kind of wondering how many people might show up, given that it's the middle of the summer quarter. But I'm really pleased that you could all make it. So we'll be talking about injection-induced seismicity today. And really the reason why induced seismicity I've been so fascinated with it over the last few years is because it offers some really interesting and unique perspectives on learning about the physics of earthquake rupture. And I hope that will be evident throughout the talk today. Now, of course, induced seismicity is not a new phenomenon. There have been well-documented cases in the scientific literature throughout the last 3 or 4 decades at least. One of the most famous examples of induced seismicity occurred in 2006 in the town of Basel, Switzerland, when actually a geothermal energy project was canceled after a magnitude 3.6 earthquake was triggered during hydraulic stimulation treatment at the site. More recently in the United States, induced seismicity has been gaining visibility and is becoming more important. And in fact, in the year 2014, it was the first time in recorded history that there were more earthquakes, magnitude 3 and larger, in the state of Oklahoma than actually occurred here in California. Now, of course, because there is some potential for damage to property, infrastructure, even hazard to human life, induced seismicity comes with a lot of consequences. And so just for example, this year, the Oklahoma Corporation Commission, who is in charge of regulating oil and gas activities in Oklahoma, decided to issue really an unprecedented mandate to reduce injection of wastewater disposal across a large part of the northern part of the state, and that actually affected over 600 wells. So from an engineering perspective, it's really important to characterize and quantify seismic hazard. And the U.S. Geological Survey, for instance, releases these types of seismic hazard maps. And this year, for the first time in that agency's history, they decided to release a version of the map that included the effects of induced seismicity. And what this map is showing is that the areas in red are parts of the country that are forecasted to have a 1% probability of experiencing a damaging level of ground motion resulting from an earthquake in the next year. And this type of analysis is really relies upon the statistics of earthquakes that have happened in the past. And furthermore, it assumes stationarity. So that is the earthquake statistics that drive the model are assumed to remain constant throughout the period of the forecast. Now, because induced seismicity is related directly to the way that we're injecting fluid into the subsurface, these models could be improved by incorporating some operational data. But it's actually more difficult than you might imagine at first glance. So really one of the fundamental drivers of my research work has been to develop a more physics-based understanding of the interactions between fluid flow and the mechanical deformation of faults and fractures in the subsurface that can host earthquakes, ultimately with the eventual goal of informing seismic hazard. And throughout my work, I made extensive use of numerical modeling techniques, and my overall approach really was to use field data, field observations to develop some interesting hypotheses and conceptual models of the types of processes that might influence behavior in the subsurface, and then to use the numerical models simply as a tool to test and validate those hypotheses. So in my talk today, I'm going to cover just briefly, the numerical model that I used and developed through part of this work, and then I'm going to just present the results from 2 case studies where we used modeling to try and learn something about behavior at these 2 real sites. So I'm not, unfortunately, going to be able to cover everything that was included in the dissertation, and I'll just touch very briefly at the very end on some of the topics I won't go over today. Okay, so let's just jump right into it. The numerical model that I used coupled fluid flow in fractured and faulted porous media with the mechanical deformation of fractures and rock, and it also included components in the model to understand different rock failure processes like shear slip, earthquake rupture, and hydraulic fracturing. So today I'm just going to cover the fluid flow portion of the model. The other components are covered in detail in the dissertation. And really, if engineers are interested in understanding how flow occurs through the subsurface, one of the most common tools that they use is called discrete fracture model. So you might have some knowledge of what the geologic structure of your reservoir may look like, and if you're interested in simulating flow through your model, you typically use what's called conforming unstructured mesh, where you explicitly put the fractures in the model and then mesh the surrounding rock with these kind of triangular meshes. So when you have a lot of fractures, you can see in some of these areas that have closely spaced fractures, you result with a lot of small control volumes that can add a lot to the computational cost of the model. And if you're interested in learning about things like fracture propagation, it's possible in this type of model, but it can become prohibitive from a computational standpoint. So really for those purposes, we tried to just avoid the use of traditional discrete fracture modeling, and we opted instead to use what we're calling an embedded fracture model. It's also just an extension of a finite volume approach, but the key idea in embedded fracture is that you treat the fractures and the matrix rock as 2 separate computational domains that are somehow coupled, and you'll see we couple it with just a source term that looks like a well. So I have the blue lines are my simple fracture network, and I'm just overlying the matrix grid on top of it, and you'll see that here I'm just showing it as a simple structured Cartesian mesh, and any place where these 2 domains overlap, they simply just pick up this coupling term. And like I said, we'll go into it in more detail on the next slide, but the coupling term really just looks like a source term, the way that we treat a well in a traditional reservoir simulator. So now as new fractures propagate through the reservoir, simply just turn on a source term just like we turn on a well in a conventional model. So what does this look like from a mathematical perspective? Here I'm just writing the mass conservation equations for single phase flow in the matrix and the fracture domain separately. And what you'll notice is that just in addition to your usual terms related to flux, wells, and storage, you have this additional coupling term related to the mass transfer between the 2 domains. And the way I've written it here, you'll see it looks exactly like the way that we treat wells. It's just related to a pressure drop multiplied by a transmissibility. That transmissibility looks a lot like the well index, and it just depends on things like the hydraulic properties of the rock and some geometrical effects. So we use this embedded fracture model not only for the fluid flow portion of the model, but also to model heat transfer. And like I mentioned, we coupled this in a fully coupled framework with fracture mechanics that was based on a boundary element approach. Now, of course, because the embedded fracture model introduces some additional approximations beyond traditional finite volume approach, I thought it might be useful to share some of the verification studies that we performed. So the first study I'm going to introduce just looks at fluid flow and heat transfer through fractured porous media. The problem involves an injection well and a production well that are connected by several parallel fractures, and ultimately the goal of the problem is to understand how the water in the fractures heats up as it flows through the hot rock, and also how that's coupled with the heat conduction in the rocks surrounding the fractures. So Gringarten, it's actually a pretty difficult problem involving a moving boundary condition, and Gringarten solved it analytically with Laplace transforms. So we also solved it with the embedded fracture approach and found that the two models agreed really quite well. I'm just plotting here the dimensionless production temperature over dimensionless time for several cases with different fracture spacing. And the solid lines are the analytical model, and the circles are the numerical model, and you can see that they agree quite well. So in this next example, it doesn't involve any heat transfer, but it does involve a tight coupling between the fluid flow and mechanical deformation of the fractures. So in this problem, we performed injection into this horizontal well into a relatively complex fracture network at constant pressure injection condition. And as flow occurred through the reservoir and fractures slipped, their transmissivity was correlated with the amount of slip that occurred. There's no analytical solution for this type of problem, so we compared with a discrete fracture model approach with the conforming mesh. And overall, we found that with sufficient discretization, the embedded fracture model was able to capture the behavior quite accurately relative to the discrete fracture model. In this plot, it's just injection rate at constant pressure over time. And so these upticks that you see in the injection rate are related to the shear stimulation events as fractures slipped and their permeability was enhanced. An attractive numerical property of the embedded fracture model is that it is convergent upon refinement. So we performed some grid refinement studies and found that with sufficient refinement, indeed the solutions converge. Okay, so the last example I want to show you is a hydraulic fracturing problem. This just looks at considered propagation of a single mode 1 KGD type fracture. So the fracture has a fixed height, and we're interested in understanding how the length of the fracture evolves over time during constant rate injection. And again, we compared against the discrete fracture model and several semi-analytical models and found an overall good agreement. There is a little bit of mismatch here, which was actually expected given the different underlying assumptions of the numerical and analytical models. And it's also worth pointing out that there are several different types of KGD semi-analytical models in the literature. They each predict variation in fracture length on the order of 10%, and our models fell within that range. So hopefully with those examples, I've demonstrated that embedded fracture is a really novel and interesting way to couple flow and fracture mechanics. It's accurate, it can be efficient, and it's especially efficient for fracture propagation problems. So really the embedded fracture was integral in this following study that I'm going to talk about, which was looking at the Fenton Hill EGS Enhanced Geothermal System project. So for those of you who don't know, EGS is an idea where you want to exploit geothermal energy from hot rock that has intrinsically low permeability, so it requires hydraulic fracturing. Fenton Hill was the very first EGS project in the world. It was operated by Los Alamos National Laboratory. And ultimately, it was successful from a technical perspective. They were able to circulate fluid and generate electricity. But there was some dispute at the time as to what was actually occurring in the reservoir during the stimulation treatments. Were these vertical hydraulic fractures propagating through the formation? This was actually the original design of Fenton Hill. Others believe that perhaps it was shear stimulation that was dominating the overall stimulation process, where slip-on natural fractures increase their permeability. And really, if you look at the data, there are two contradictory data sets that these different groups were using to support their ideas. So first, injection was occurring at pressures that exceeded the fracturing pressure during all of the stimulation treatments. So that would suggest that hydraulic fractures indeed may have been forming in the reservoir. But they were actually not able to observe directly any new hydraulic fractures at the wellbore. And furthermore, there was actually a lot of seismicity generated during the stimulation treatment, and the overall pattern in seismicity was not aligned with the direction of the maximum principal stress, which commonly happens during hydraulic fracture jobs with large planar fractures. So in this work, we hypothesized that in fact what was occurring in Fenton Hill was a mixed mechanism stimulation process. And I'll go into the details of what I mean by mixed mechanism, but overall, the modeling results that I'll demonstrate here in the next few slides were consistent with most of the characteristic traits of the observational data at Fenton Hill. Specifically, there was low injectivity at one of the wells up until reaching a critical threshold pressure. And this was consistent over multiple stimulation treatments in the well. But in fact, that near wellbore injectivity enhancement was not permanent. And then, like I said before, the overall migration of the seismicity at the site was not aligned with the direction of the maximum principal stress. So Fenton Hill was a geothermal reservoir located about 3.6 kilometers deep. It's 230 C. There were actually 5 stimulation treatments that occurred, 4 of them in one well, 1 in another, and then there are also 2 long-term fluid circulation experiments. This all occurred over a period of about 20 years, and we simulated each of these components of the field project. And it's important to understand how we arrived at our mixed mechanism conceptual model, so I just want to walk through, in the next couple of slides, some of the data sets that we used to constrain our conceptual and numerical models. First of all, it's always important with this type of problem to frame it in the context of what we know about the state of stress. And fortunately, at Fenton Hill, there was a lot of field experiments that were performed to measure the state of stress. There were wellbore breakouts and mini frac tests. So we had reasonably good constraints on the stress orientations and the stress magnitudes at depth. We had access to the rate and pressure data from each of the stimulation treatments as well as the fluid circulation experiments. And one of the most interesting observations that we found while looking at this data was this consistent pattern of extremely low injectivity even at the lowest flow rates. That's characterized by these really sharp pressure increases over time. And then upon reaching this kind of critical threshold pressure of about 5,500 psi wellhead pressure, injectivity increased dramatically. And so further increases in the injection rate were only followed by modest pressure changes. So that was something that we wanted to try and capture in our model. The seismicity at the site was really one of the most important components of the data that drove our conceptual model. Based on the direction of the maximum principal stress at the site was north 30 degrees east, and you can see that the overall migration of the seismic cloud really did not followed more of a north-south pattern. So that's significantly different than you might expect if a large planar fracture was propagating in the direction of the maximum principal stress. And there were also several focal mechanism analyses that suggested that perhaps slip was occurring on near vertical fractures And one of the nodal planes suggested that they could be oriented north 30 degrees west. And finally, we had access to wellbore temperature logs, and these are important just because they indicated that flow was occurring at several discrete intervals over the open hole section of the well. We use that to justify our discrete fracture modeling approach. So in our conceptual reservoir model of Fenton Hill, there was a dominant set of natural fractures that were oriented at roughly north 23 degrees west. And that orientation was not arbitrary. It happens to be the fracture orientation at which fractures bear a normal stress of about 75 megapascals at depth, and that's corresponding directly to that 5,500 psi wellhead pressure, the rollover threshold pressure. We hypothesized that stimulation occurred through a mixed mechanism process where fractures opened as fluid pressure reached their normal stress, and hydraulic splay fractures propagated off tips of the natural fractures. So just a quick note on what this mixed mechanism stimulation idea is. If you have fractures that are oblique to the principal stresses, as they slip, concentrations of stress near the fracture tips will encourage new hydraulic fractures to propagate in the areas of increased tension. And in fact, you see this all the time in nature. This is an example of several parallel fractures in sandstone with splay fractures coming off their tips and linking up the neighboring fractures. And on the right, that's a picture I just took on Sunday as I was backpacking through the Sierras. And again, this is actually in granite, and you can see that you have these two parallel fractures with some consistent splay fractures forming off to one side. And that's the exact mechanism that we're hypothesizing occurred at Fenton Hill. So just want to run through a quick video that demonstrates the results of the 4 stimulation treatments in one of the wells. So in this video, what you're seeing are the black fractures. The black lines are the natural fractures. The red lines are the hydraulic splay fractures that are propagating off of the natural fractures and terminating against their neighbors. And the black dots are the microseismic events that are associated with slip predominantly on the natural fractures. And what you'll notice is that the splay fractures are propagating, as you would expect, in the direction of the maximum principal stress. But because they're able to terminate against their neighbors, it results in an overall north-south migration pattern of the stimulated zone, which was consistent with the observations. And I just want to point out that the idea that fractures are able to terminate against their neighbors was a model assumption here. So fractures were able to terminate 50% of the time. We specified that, the jury is still out in terms of understanding the exact physical mechanisms that control hydraulic and natural fracture interaction. But in this model, it was entirely necessary that they did so in order to control that overall migration pattern. And, just want to point out that overall our spatial extent of the seismic cloud was very similar to that which was actually observed in the field. Another way of interpreting the seismic data is to look at how the rate of propagation away from the well over time. So in this plot, I'm just showing the actual field data, and the points are the distance relative to the well of each seismic event over time. And I just want to point out several interesting parts of the data set. At early times, you see a lack of data. This is just for the 4th treatment, and so that's related to the Kaiser effect. This lack of data here was an acquisition problem, so that's not real. But during injection, the events tended to occur across the entire stimulated zone, and it could be characterized by kind of bursts of seismicity. And following shut-in, in fact, what was observed was that the events occurred to be tended to be confined towards the edges of the stimulated zone. These are the model results of the seismicity that we calculated as the fractures deformed. And again, we were able to capture the Kaiser effect. These bursts in seismicity corresponded to times when hydraulic fractures linked up new zones of natural fractures, and they were able to kind of slip sporadically at those points. And we also were able to capture this post-shut-in behavior. In terms of the rate and pressure response at the wells, we observed relatively good both quantitative and qualitative results. So one of the most important parts that I want to draw your attention to again is we were able to capture that low injectivity followed by a marked increase at a very specific threshold pressure. And in the model, that was entirely related to the ability for the natural fractures that intersected the well to open as fluid pressure reached their normal stress. So it's really that nonlinear coupling. Here I'm showing the rate and pressure results from the fourth and largest stimulation treatment. And again, you see the pressure rollover behavior. And I'm pointing out that it's the fourth treatment just to reiterate the fact that this change was reversible throughout each of the stimulation treatments. And so in our model, we had to use a shear dilation angle of 0, which suggests that perhaps shear stimulation at Fenton Hill was not a dominant mechanism in terms of permeability enhancement at the site. So I just went through the stimulation phase of the modeling. We also modeled the circulation phase, the 2 circulation experiments. And I don't have time to go through all the details of those results, but I do just want to bring up one interesting observation. So at Fenton Hill, they performed several successive tracer tests during the circulation experiments, and the results of those tracer tests suggested that the reservoir volume, the fluid accessible volume, was growing over time. And if you look, what I'm showing in this plot is both the surface area and the storage volume of the stimulated fracture network plotted as a function of cumulative injection volume, which is really just a proxy for time. And if you look at during these last 2 stages, during the long-term circulation, what we're seeing is that there isn't much change in fracture surface area, but the volume is really increasing over time. And again, that's that nonlinear coupling of as fractures are able to dilate, even during relatively kind of steady state operations. And furthermore, what's really interesting about this plot, I think, is that I've separated both of the surface area and volume into the components that are related to hydraulic and natural fractures. And the storage volume, you'll notice, is essentially entirely dominated by the natural fractures. Whereas the fracture surface area is dominated by, sorry, I have that in reverse. The storage volume was dominated by the hydraulic fractures, but the surface area was dominated by the natural fractures. And that can have really significant consequences when thinking about how to design a reservoir engineering strategy for operating an EGS reservoir. So just to summarize this portion of the talk, we performed modeling at Fenton Hill, and since our results were consistent with several of the characteristic traits in the field data, it suggests that perhaps our model is useful for learning about the reservoir. So the results suggest that indeed the mixed mechanism hypothesis is a plausible explanation for these contradictory data sets at the site. And we should admit that this may not always be the dominant process in all reservoirs. It might depend on lithology or the state of stress. But since it appears to be a real mechanism, it would make sense to design reservoir engineering tests that are able to diagnose stimulation mechanism early on in a project's life. And furthermore, just having a broader understanding of these nonlinear processes that that occur during EGS reservoir stimulation projects can also inform seismic hazard analysis and mitigation strategies. So I'm going to transition away from geothermal and take a look at the magnitude 5.6 earthquake sequence that occurred in 2011 near the town of Prague, Oklahoma. So this is really the largest earthquake that has been to date associated with wastewater disposal. So it's really important to understand some of the processes that were involved in this sequence. And just taking a step back and thinking more big picture, if we want to apply physics-based models to seismic hazard analysis, then we have to know something about the actual processes that we need to model and the actual hydraulic and frictional properties of these large faults. But the reality of the situation is that these faults are very large, on the order of at least 10 kilometers, and they exist in the basement rock beneath the aquifers that we're actually targeting for fluid injection. So it's really impossible to use kind of traditional reservoir engineering techniques like well testing to try and get at what some of these properties may be. So I attempted to use modeling to get at this issue. And really the key observation at the Prague sequence, at least for the purposes of this study, was that the main earthquake, which was that 5.6 event, was actually preceded about 20 hours earlier by a magnitude 4.8 earthquake in very close proximity. And what I did was investigate the relationship between these two events in order to understand something about the in situ behavior of these large basement faults that can host damaging earthquakes. The hypothesis that I worked under was that the main earthquake was actually triggered by the static stress change that occurred during the first event. But because there was this delayed 20-hour delay, that suggests some transient process was involved. And so what I proposed was that it was a hydromechanical response that may have acted to dampen the Coulomb stress change, which involved an instantaneous undrained response to the change in stress felt by that main fault, followed by transient fluid flow, which acted as a loading term. In this part of the study, we used a rate and state friction constitutive model to model earthquake rupture. And really one of the most important parts of this study was to try and understand what the actual geometry of the fault structures looked like. And so we did that by based off of distribution of the aftershocks that occurred during these two earthquakes, as well as looking at the focal mechanism inversions. We were also fortunate to have access to some of the analyses performed by students in the Stanford Center for Induced and Triggered Seismicity. Most importantly, Raul Walsh provided his analysis of focal mechanism inversions of 14 nearby earthquakes to arrive at constraints on the stress orientations and the stress magnitudes at depth. We modeled the system as this set of two faults that were two-dimensional vertical faults located at roughly 5 kilometers depth. And in the study, I was really only interested in understanding how fluid flow along the fault zone structures occurred. So because it was only 20 hours and because these faults were located in the basement rock and surrounded by low permeability rock, I neglected flow in the surrounding rock and was, again, really only interested in flow along the fault zone structures themselves. We modeled the foreshock as a magnitude 4.8 event that resulted from a uniform stress drop of about 1.7 megapascals. These are, what I'm showing here are contours of the changes in stress that occur in response to that initial earthquake. These are the stress components in the Cartesian coordinate system. If you rotate those stresses and resolve them into their shear and normal components acting on the main fault, this guy, these are the resulting changes in normal and shear. And what you'll notice is that right here ahead of that fault A crack tip, the fault B is actually experiencing a reduction in normal stress. So that's an unclamping type of behavior. And in terms of the shear stress, you actually see an increased shear. And both of those processes encourage earthquake rupture to occur. So the actual stresses that the main fault felt in the model were on the order of about 2 megapascals. Of course, they dropped off. The stress perturbations dropped off over distances of about 1 kilometer. And again, I just want to point out this kind of unclamping behavior that occurred over parts of the fault. In this slide, I'm just going to walk through some of the theory that really drove the analysis. Here I'm just writing the one-dimensional single-phase flow equation for flow along faults. The flux term is related to the transmissivity of the fault, and the storage term is related to the void aperture or the porosity of the fault. And in this study, really the hydromechanical coupling arose entirely due to our use of this nonlinear joint stiffness relationship. It's a constitutive model, empirical model, that was really developed based on laboratory experiments of fractures. Of course, you can think of a large fault zone as a structure that involves a lot of connected fractures. So using that relationship, you can actually define a fault compressibility or compliance. And in the undrained limit, at very short time spans, the flux term on the left of the fluid flow equation vanishes. And you can introduce your fault zone compressibility equation to somehow to kind of linearize the storage term on the right. And what you'll arrive at is just an approximation for the change in fluid pressure that can be expected to occur within the fault zone structure given a change in normal stress. And so I mentioned earlier that the Coulomb stress change in this hypothesis was responsible for driving earthquake rupture, and it's influenced by changes in shear, normal stress, and fluid pressure. And what happens is that for very compliant faults, the change in normal stress is associated with a more or less equal change in fluid pressure, and they essentially cancel each other out. For stiffer faults, the change in fluid pressure only partially mitigates that normal stress change. Of course, once fluid pressure gradients in the fault zone set up, that encourages fluid flow to occur, and over time, pressure will begin to equilibrate in the fault zone, and that can act as a transient loading mechanism in terms of the earthquake rupture problem. I mentioned that we used rate and state friction in this model, and so that allowed us to calculate accurately the transition from slow sliding or stuck faults up to rapid sliding when the earthquake has nucleated and begins to rupture. This is a typical numerical result showing the evolution of sliding velocity over time at the main shock nucleation site. And it can be characterized by an initial jump in sliding velocity due to the initial static stress change that the secondary fault felt. So that's mostly the shear stress effects. This kind of middle portion of the nucleation phase can be characterized by both changes, transient friction changes, as well as that transient loading caused by the hydromechanical effects. And then finally, rapid acceleration occurs, and then that's when the earthquake has actually nucleated and begins propagating as a sustained rupture. So in the simulations that we ran, we actually observed that the hydromechanical effects could affect the time to instability of of the main shock quite significantly. So just remember that the main event, if this event B, occurred about 20 hours after the initial foreshock, and for faults with very low transmissivity, that tended to delay that transient flow behavior, and the time to instability tended to be overestimated. For higher transmissivity faults, kind of the reverse process happened, and time to instability tended to be underestimated significantly. And similarly, for stiff faults, the initial change in Coulomb stress was enough to kick that kick the rupture into the nucleation phase quickly. And so really by varying these hydraulic properties, we were able to arrive at some constraints in terms of the actual hydraulic properties of these large types of basement faults. So overall, our goal was in this study, was to develop constraints both on the types of behavior that can influence earthquake rupture in large basement faults, as well as to arrive at some idea about what the actual values of the hydraulic properties may be. The study was informed by a lot of prior work that had been done at the site, which was really important. Our results suggested that hydromechanical effects could, in fact, explain the 20-hour delay. But of course, there's a lot of non-unique parameters that can influence the time to instability. So we weren't able to arrive on one particular set of properties that we would call the answer. But it was useful for just developing more general constraints on what some of the properties may be. And that'll be helpful for informing future physics-based seismic hazard analyses. So just to bring it back full circle, at the beginning of the talk, I mentioned that my overall research theme was to try and develop these improved physics-based understanding of the relationship between flow and fracture mechanics, ultimately to inform seismic hazard. And I was able to accomplish that by developing a numerical modeling platform that coupled fluid flow and fracture mechanics. And I applied that model to interpret field data at several specific sites in order to arrive at some constraints on in situ properties and some of the relevant physical processes that can occur. I was not able to cover two additional studies that are included in the dissertation. One looked at seismicity in unconventional hydrocarbon reservoirs, and another study was a more theoretical study looking at the link between injection and some of the more important statistical properties of earthquake sequences that can influence the seismic hazard models. So that ends the technical part of my talk, and I just do have a couple of acknowledgements that I would like to make. First, of course, my advisor, Roland Horn. It's really been a pleasure working with you over the last 4 years. Really, one of the qualities that I admire about Roland the most is that he is just so dedicated to each of his students and to seeing each of us succeed. He really does an awesome job at setting us up for success and then letting us finish the job. So it's really, like I said, it's been a pleasure and an honor to work with you. Mark Zoback, it's been really a fun time being part of SCITS since its inception there a few years ago. I've been able to attend every SCITS meeting up until this point, so I hope to come back and maybe add some more to SCITS in the future in a different capacity. Of course, Eric Dunham, thank you for all the discussions we've had and encouraging me to work with your group and some of your students. It's been a big help. And Dave and Lou, thanks for joining my committee today. I've been a part of two research groups, Stanford Geothermal Program and Stanford Center for Induced and Triggered Seismicity, and it's really been a pleasure working with all of the students involved in both of those groups. I just want to acknowledge the financial support of the industrial affiliates of the Stanford Center for Induced and Triggered Seismicity, as well as the US DOE Geothermal Technologies Office for supporting the Fenton Hill study and really encouraging a lot of useful collaboration with other research groups across the country throughout that project. The research probably definitely would not be possible without the help of Mark McClure, so thank you very much for all the hours we spent brainstorming and debugging code and everything. It's been a lot of fun. Thank you. And of course, all my family and friends here in the ERE department, just to name a few, Jacob, Phil, and Bryce, Soon, Charles, and Michael. And last but not least, it's really, becomes a lot easier to get through some of these more critical parts of your life when you have a lot of support from your friends and family. Thanks to Abby Ruckshanes, who's here today, as well as my two sisters, Mia and Dagny. And with that, thank you very much.
Okay, now's your opportunity to come up with some questions and comments on the presentation.
Yeah, Jack, your work on Fenton Hill was new to me, so I found that really interesting. And the Kaiser effect, you showed there something that's also been seen, for example, at Paradox Valley, where they don't get any injectivity in each other to get back to the crack pressure. What do you think is controlling the elevation? What is physically causing the Kaiser effect, you think, at the Fenton Hill site?
Yeah, so the question's about the Kaiser effect, which is just, I don't know where the term originally came from, but it generally describes the lack of seismicity that you see early on in stimulation projects. And in the model, it's really just due to the fact that because those fractures have already experienced slip and have experienced some stress drop, the shear stress left driving those fractures is now lower than it was initially. And so in order to get them to slip again, you have to increase fluid pressures beyond what was observed during the prior stimulations. And in that last stimulation treatment, the injection pressures kind of were the highest that they had ever been throughout the project.
Thank you for excellent presentation. I noticed your ETFM and DFM model match pretty good. How do you compute this transient transfer term, numerically or analytically?
Yeah, so the question was about how to calculate the fracture index, the analogous to the well index. And the idea is that, you can calculate it analytically by essentially showing that you have, you want your mass flux to be a transmissibility times a pressure drop, and then you write an equation just using Darcy's law to show how, and you make the assumption of linear flow in the vicinity of the fracture. That's really the key assumption there. And by comparing the equations, you'll see that it just really depends on things like the fracture geometry and the matrix control volume geometry and matrix permeability. And we calculate it analytically, but for complex geometries, we just use a numerical integration that's involved in part of the calculation.
And for numerical integration, did you use a global solution or you use localized boundary conditions?
Oh, so it's not a numerical integration involving some sort of like upscaling procedure. The numerical integration just is used to determine one specific part of the term. It's not as complicated as that.
Other questions? How about a question from a student or two? Gosh, Jack, you're definitely speaking.
Stumped him.
Well, that's it. Let's thank Jack again. You're all excused.
Thanks.